Yeah, good morning, every one of you. So, until the last class, we are seeing this
Good
diffusion
morning,
unit.
sir.
Hi, good morning. We are seeing this diffusion unit. So, in this one, some of the basics we have covered and the contents we have discussed. What is the definition of mass transfer? How important the diffusion, whether it's a molecular diffusion or eddy diffusion, we have discussed so far. So, today we will see this one various mass transfer processes. So, mass we are seeing transportation. What is a mass transfer? Mass transfer is nothing but transportation of mass from one region to another region or one phase to another phase or from one location to another location. Okay, we are also as a human body, we are also one type of mass. Okay, this mass is getting transported from our home to college. Is that a mass transfer? No, it is not a mass transfer. Okay, though we are coming by traveling or something else, this is also traveling, but we are macroscopic view. In a big picture, we are seeing that we are traveling from one location to another location. That can't be a mass transfer. There are many examples that defines what is a mass transfer, especially the industrial processes like absorption. Okay, AB, absorption, which is classified as a gas to liquid operation, is a mass transfer. Then extraction, which is classified as a liquid to liquid. Don't worry, I will say what is this gas to liquid, what is this liquid to liquid. Okay, that I will define in detail. Then this is leaching. Next one is a leaching, is one type of mass transfer operation in which it is classified as a solid to liquid operation. Then adsorption. Okay, this is AB, this is AD. Adsorption, which is classified as a fluid to solid operation. Then membrane separation, whatever the purified water nowadays we are drinking, RO water or UV treated water, all these waters uses this membrane processing technology or membrane separation process. That is also one type of mass transfer operation. Then humidification, whatever the humidity that we are facing now in the summer, humidity will be very high in the especially in the coastal areas, humidity will be very high. Okay, so how we are facing that one, that is also due to humidification. So that is also called as a mass transfer operation, which is classified as liquid to vapor phenomena. Then next, evaporation. So all this humidification, evaporation, crystallization, drying and distillation, all these operations are known as simultaneous heat and mass transfer. Heat and mass transfer will be responsible to carry out this type of operations. Then evaporation, you may be seeing this evaporation in heat transfer. Okay, evaporation is nothing but removal of large amount of water. Okay, for example, concentration of juices. Okay, in which in the juice what happens, much amount of water will be there. So removal of large excess of water is known as evaporation using thermal means. That is also one type of mass transfer operation. Then crystallization. So in the crystallization, what happens using this mother liquor, and as a example we can take sugar preparation. Okay, in the sugar preparation, what happens, from the cane, sugar canes, we will be extracting the juice, sugar cane juice. That sugar cane juice will be heated to the saturation point or super saturation point. Then what happens, that liquid will be converted to solids. So that is called as a crystallization. So that is also mass transfer operation. Then next is drying. Okay, removal of very small amounts of water. Okay, especially the moisture removal is known as a drying. So that's the difference between evaporation and drying. Evaporation will remove large amount of water, whereas drying will remove very trace amounts of water, minimum amount of water. So that is a drying. Then next one is a distillation. So it's a very important mass transfer operation, distillation. In the next 2 units, you are going to see in detail what is a distillation. Based on the boiling points of the constituents of a mixture, the separation of a mixture is known as a distillation, or based on the relative volatility of the constituents present in a mixture is called as a distillation. So what is this gas to liquid, liquid to liquid, solid to liquid, fluid to liquid? We will see in detail now. So okay, we have to derive this one also. We'll do this one. First, we will see what is the solid to liquid, liquid to liquid. Okay, examples of mass transfer operation. Examples of, I am writing in a short form, MTO. Examples of mass transfer operation. First one, we are defining that absorption, AB, absorption. This is important. Okay, absorption. Absorption, we are telling this is a gas to liquid operation. So what is this gas to liquid operation? Usually in the absorption operation, you may be seeing this absorption operation in mass transfer operations too in the next semester. So just quickly, I will try to revise this one. So what happens? Usually the gas mixture will be there. Gas will be there in which solute will be there plus carrier will be there. So carrier means in the gas, these two are the gas phase only, present in the gas phase only. But we have to remove the solute from this gas phase. How to remove this solute? We will be giving some solvent. We will be just giving some solvent to it, which is nothing but liquid. Okay, this liquid will solubilize the solute which is present in the gas, as the gas is moving from the bottom to top and the solvent or liquid is moving from the top to bottom. So there a interchange will be happening here in between this liquid and gas phase. Then a carrier, okay, ideal case, a carrier will be coming out, leaving behind all the solute to the liquid. Then here, whatever the solvent which we have given, solvent plus whatever the solute which is there in the gas which is coming. This is known as absorption operation. So here why we are saying this gas to liquid operation means the solute which is present in the gas phase is getting transformed or it is getting transferred to liquid phase, which is nothing but solvent. So because of this reason, we are saying this is gas to liquid operation. So example of this mass transfer operation, absorption operation is nothing but removal of NH3, okay, ammonia, removal of ammonia using water as a solvent, or some acidic gas like HCl, H2SO4 can also be used as a gas, as a liquid solvent phase. So this is the best example for absorption. Then next operation is extraction operation. Next is extraction. So we have seen earlier also this one. Extraction is referred as liquid extraction. Usually LLE, we will say LLE, liquid extraction. Why this is liquid? So in the extraction operation, what happens means, so the feed will be going like this. So this is a feed in which solute will be there plus some carrier liquid. Okay, this is in liquid phase. All these are in feed is in liquid phase. Then using a third component, okay, that is known as a solvent. So which is also in liquid. Okay, then this liquid, when they both are miscible with each other here, okay, they are getting in contact with each other, then what happens? They both will be solubilizing in each other. Then it will be leaving behind some extract, some raffinate. So here the role of extraction is to separate this solute, okay, the liquid solute in this solvent. Okay, either of the phases it will come as a solvent plus liquid and carrier plus some solvent. Like this it will be coming. So because of this, all the phases are present in the liquid only. So because of this reason, we are referring to as liquid extraction. Okay, liquid extraction. Like the example is this extraction you will find in pharmaceutical industry. Removal of some pharmaceutical growths. Okay, which can be the good example for this liquid extraction operation. Or we can say one more example is this one. What we say? Separation of aromatics. Okay, separation of aromatics from kerosene. Okay, kerosene based components or kerosene based fuel oils is the best example for this extraction operation, in which aromatics will be separated from the mixture of kerosene plus aromatics using some suitable solvents. Is the best example to describe what is the extraction operation. Okay, because of this reason, every phase is in liquid phase, so that is called liquid operation. Then third one is a leaching. Okay, so leaching is also known as a solid liquid extraction. Okay, this is also extraction, but where it is extracting the solid to liquid, the phase is getting transformed. Why it is solid to liquid? I will explain that one. See here also some leaching operation will be there, in which feed will be given. Okay, usually this feed will contain some solute plus carrier, or we can call that carrier as a inert. Okay, this feed phase will be present in solid phase. Okay, solid phase. Then this solid will be solubilizing in some solvent. Okay, this phase is in liquid phase. Then once again a raffinate or extract will be obtained. Okay, for example, the best example for this leaching operation is extraction of oil from oil seeds. Extraction of oil from oil seeds. Or another example we can write extraction of coffee from coffee beans. Extraction of coffee from coffee beans using hot water as a solvent. So in this case, using oil seeds, using some solvent like we can use hexane or petroleum cut fractions, whatever the hexane like type of components are there, we can use to extract the oil. For example, with this example I will refer. So oil seeds are entering, like sunflower oil seeds. Okay, oil seeds, sunflower oil seed, for example, we will take. So after crushing that sunflower oil seeds, that crushed oil seeds will be sending inside the leaching operation, and here the hexane as a solvent will be used. Then the hexane plus this oil seeds will be miscible with each other. Okay, mingling with each other. Okay, then after mingling, what happens? Whatever the oil which is present in the sunflower oil seeds, that will be transformed to the solid phase, or that will transformed to the solvent phase. Then solvent plus liquid will come as a raffinate phase. So that is here solvent plus oil will be coming here. Here the seeds, okay, whatever the inerts which are there in the seeds, okay, solute is nothing but oil only, okay, which is coming like this. So because of this reason, the solute which is present in the solid phase is getting transformed to the liquid phase. So because of this reason, we will call this as a solid to liquid operation. So this is the leaching. Then next one is absorption.
Sir, unable to hear
Yes.
your voice.
Now,
Now, okay, sir.
okay. Earlier, you couldn't listen anything.
Just 30 seconds back, sir.
Okay, okay. Yeah. Do you catch this point? Leaching.
Yes, sir.
Shall I explain once? Okay. Then I am continuing from absorption. So this is you just consider as a AD, absorption. Okay. What is this absorption? Why this absorption is called as a fluid to solid? So what are the fluids which are there? F means fluid. The fluid is nothing but liquid phase, or gas phase is nothing but fluid. So here what happens in the absorption process, usually some fluid will be there. Okay, gas or liquid. So in this fluid, solute will be there. So which we are concentrating, which we have to separate, plus some inert or carrier gas will be there. So that's inerts or carrier gas. So we have to leave behind this one and separate out this solute. How do we separate? We will be applying some pressure. Okay, we will be passing this through some solid. Okay, whenever this phase is just fluid phase is just attaching to the solid surface, it will deposit the solute components onto the surface of this solid like this. Okay, here the solute which is present in the fluid phase, whether gas or liquid, is getting transformed to the onto the solid surface. So because of this reason, we are telling this as a fluid to solid operation. So that is this adsorption operation. For example, you can take the removal of dye. Okay, removal of dye is the example, best example for this one. Removal of dye from aqueous solution using carbon, activated carbon or charcoal. Activated carbon or charcoal is the best example for this one. So how do we remove the coloring components? For example, this is a beaker. Okay, in this beaker there is some water. Okay, which is contaminated with some color. Okay, for example, this is some blue color. Okay, this water is contaminated with blue color. We have to remove this blue color. How do we remove that one? We will be just depositing some activated charcoal or activated carbon into this one. So when you deposit or when you throw some activated carbon particles into this contaminated water, what happens? It will absorb. Okay, this whatever the blue color is there. For example, this is one activated carbon particle. Then this blue, whatever the blue color is there, that will be attaching to the surface of this solid and leaving behind the liquid, pure liquid or a colorless liquid. Okay, pure liquid or colorless liquid as a as a pure liquid, it will be leaving behind. Okay, I will show one picture maybe there here. Okay, no picture is there. Okay, in the couple of classes I will show that picture. So generally this is the phenomena which will be happening here. So whenever you throw some particles of activated carbon into the contaminated water, what happens? The contaminations will be just attaching to the surface of the solid. So because of this reason, earlier before what happens? The contaminants are present in the liquid phase. Then after the adsorption operation, the contaminants will be present in the solid phase. Okay, this is liquid to solid operation. When this phenomena is happening in the gas phase. Okay, when such phenomena is happening in the gas phase. Okay, in the gas phases, what happens? Usually we will apply some pressures. Okay, gas phase. For example, this is a gas phase. Removal of CO2. Okay, removal of carbon dioxide plus some air is there. For example, if you think this is in a gas phase, then if you deposit some activated carbon, so this preferentially CO2 or some gases will be deposited onto the surface of this solid. Then in this phenomena, what is happening? Gas to solid it is taking place. That's why combinedly gas and solid or liquid are known as fluid phases. So the adsorption operation is nothing but fluid to solid operation. Here this is solid, in the liquid phase also it is solid, and here also in the gas phase operation is also in solid. So fluid to solid operation is known as a adsorption operation. So that's the reason we are calling this as a fluid to solid operation. The next example is a membrane separation. Membrane separation, we need not to tell anything about membrane separation. Okay, membrane separation is one type of filtration process. You might have seen in this mechanical unit operations, or now the classes are going on. So mechanical unit operation. So some thin membrane will be there. Whenever the contaminated water is just deposited on, it's just fed on one side of the membrane. So this will be some membrane. Okay, contaminated water just fed onto the one side of the membrane. Then what happens? Preferentially, only the water which is contaminants free will be coming out like this. Okay, leaving behind whatever the contaminant particles onto the surface here. Okay, that is called as a this fraction. The fraction of water or fraction of feed that has been passed is known as a permeate. Permeate, permeate. And fraction of feed that is retained on the membrane surface is known as a retentate. So this is the membrane process. So we will see in the mass transfer 2 in detail about this, what is this membrane process and everything. And next operation is a humidification operation. What is humidity? Humidity is nothing but amount of water vapor which is present in the surrounding air, or in the industrial sense, amount of water vapor which is present in the some gas. So that is known as humidity. So what is humidification? Humidification is nothing but addition of water vapor to the surrounding air is known as humidification. So in the humidification, why we are calling this as a liquid to vapor means, for example, there is some air. Okay, some beaker full of water is there. Beaker full of water is there. On top of this beaker, you are allowing some air to flow. Okay, this is air, this is water. Okay, what happens this when you are allowing some air to flow on top of the beaker full of water, this water will be converted to water vapor, and this vapors will be just visible with the surrounding air. This is known as humidification. That's why in the coastal regions, what happens in the coastal regions, whatever the water which is present in oceans, that will be solubilizing, or that will be adding to the air. That's why we will feel much sweat in the coastal areas because of this phenomena, which is humidification operation. So earlier the water is present in the liquid phase, and after humidification operation, the water will be converted to vapor and it will be going into the gas phase or air phase. So this is water vapor in this phase. So that's why we are calling this humidification as a liquid to vapor operation. Then next one is evaporation. Evaporation is nothing but removal of a large excess of water. So that is better to refer to as this heat transfer operation. So in the evaporation, what happens? There will be some evaporator will be there. So you will be feeding some uh, dilute juices. Okay, in the dilute juice solids plus water will be there. In this one, when you heat, when you apply some heat onto the evaporator, so this whatever the water is there, large excess of water will be converted to vapor. This water vapors will be just extracted to the outside, and this solution will be concentrated. So best example for this operation is the concentration of fruit juices is the best example for the evaporation operation. The next one is a crystallization. So crystallization we need not to explain. Crystallization. So in the crystallization, what happens? First, the sugar canes will be there. So this sugar canes will be crushed or converted into small beads. Then it will be sugarcane juice will be obtained. Sugarcane juice. Then this sugarcane juice will be converted to solids after heating to the supersaturation. Supersaturation means whatever the liquid which is there, excess of water which is there inside the sugarcane juice will be evaporated. Then after evaporation, it will be heated until the supersaturation. Then this whatever the liquid is there, after concentration, it will be converted to the solid. So that is crystallization operation. And next one is a drying operation. So in the drying operation, for example, example for this drying operation, what we can say. Okay, for example, there is some wheat flour. Okay, wheat flour will be there. So wheat flour, we have to mix in water initially. Okay, water plus wheat flour will be mixed. If you want to dry this wheat flour, okay, a dough of wheat flour, what happens? You have to put in some oven, okay, hot air oven, and you have to pass some hot air over this dough which is put on this oven. Then the trace amount of water which is present inside this dough will be evaporated by the hot air. This is the example for this drying operation. In the drying operation, the how it is different from the evaporation operation means in the evaporation also water is removing, but in the case of evaporation, large amount of water will be there, but in the case of drying, very minimum amount of water. So we will call this as a moisture only will be there. Removal of very trace amount of water vapor, water which is present in the solid is known as a drying. Removal of large excess amount of water in the solids is known as a evaporation. That's the difference between these two. The next operation is a distillation operation. Okay, what is this distillation operation? Depending on the boiling point of the mixture or boiling point of the components or relative volatility of a components, the fraction of feed which is passed through the distillation column. So this is feed through the distillation column will be separated into two products. One is distillate, which is nothing but more volatile component. So more volatile component will be coming as a top product, or we can say this is low boiling point component will be coming as a top product, that is called as a distillate. And the component which is having a less volatility, so this is residue. So the component which is having a less volatile component or high boiling point component will be separated as a bottom product or residue. So this is called as a residue or bottom product, whereas this is distillate or top product. So you might have seen the distillation, basic details in the CPP, chemical process principles. So the feed which is passed through the distillation column will be separated out into the two fractions, two products. One product is a top product, or we can call this as a distillate. The fraction of feed which is having a more volatile component or a low boiling point component will be appearing in a distillate, whereas the fraction of feed which is having a less volatile component or high boiling point components will be appeared in the residue or bottom product. So this is called as a distillation operation. Depending on the more volatility, depending on the relative volatility or depending on the boiling point, the separation happens is called as a distillation operation. So these are all the popular example for the mass transfer operation. So something is going on inside this one. We are referring this is distillate, this is residue. Okay, these two are the products, and we are referring the moisture which is present inside is getting transformed to the surrounding hot air. Okay, here we are referring the water which is present is evaporated and it will be heated to the supersaturation. Then the solids are obtaining, and here in the evaporation, the water is evaporating. Large excess amount of water is evaporating. And here in the humidification, the water which is present in the liquid phase is getting transformed to the vapor phase. All these are there. Nothing we can see with our naked eye here. Something is happening, but the end product we can measure. This much amount of moisture is there. This much amount of water is there, but we can't see what is the process which is going on inside. So realizing or quantifying what is happening inside this overall processes is nothing but a mass transfer operation. So earlier I have said we are also a mass. Okay, we as a human being, we are also having some weight, some mass inside us. So we are moving from our home to college or from college to home. So this is also transportation of mass. No, why we are not considering this is also transportation of mass? Why? Because we can see, we can move ourselves there. But here these are the microscopic scale processes. In this, there is something is happening, some transportation is happening that we can't tell, that we can't quantify using our naked eye. Okay, we have to quantify using some mathematical formulas. So dealing with this quantification, okay, microscopic scale quantification is nothing but mass transfer operation. So to quantify how much amount of liquid has been transformed to vapor phase, or here also same, how much of water is transformed to the vapor phase, or here how much amount of water which is present, moisture which is present is transformed to the hot air, okay, or the gas phase. Or here also how much amount of feed which is appearing as a distillate, how much amount of feed which is appearing as the residue. To calculate or to quantify that one, we need a mass transfer operation, in detail mass transfer equations. So to develop that equations, we need to adopt certain terminology. Okay, certain terminology means some basic units, some basic quantities. Like in the IPC, the first class I have said you, there are basic units and derived units. So similar to that one, what type of units we can use here in the mass transfer, we will be defining in the in this class. So before that, I just want to know that until here it is clear, the every operation. Any doubts?
No, sir.
Excuse me,
Yeah.
sir. Can you
Okay.
explain humidification process, sir?
Humidification process. Okay, yeah. So humidification process. So first, what is humidity? What is humidity? Humidity is nothing but kg of water vapor per kg of dry air. Okay, this is the definition of humidity. Kg of water vapor per kg of dry air. So in this humidification, what happens? This is the basic definition. Humidity means, but humidification is a operation. Means it's a mass transfer process. In this one, what happens? For example, there is a stream of water. Okay, for example, you are present in Vizag or near the Hussain Sagar. You are there. Okay, water body. There is some water body. So here the humidification phenomena is usually natural process. It will be taking place. How it is taking place? There is a water body here. Some water is moving in a stream. Then on top of this water, there is inevitable some air will be moving. Okay, air will be moving like this. So movement of air will be happening on top of water. Whenever there is a movement of air on top of water, so the part of the what we say, this liquid or water which is present in Hussain Sagar or what is maybe, so that is getting transformed to the as a vapor to the surrounding air. Okay, this is air and this is water stream. Okay, so this water vapor, okay, this initially this is in liquid phase, water is in liquid phase. Whenever it is addition which is adding to the air, then it is becoming as a vapor phase. Okay, this phenomena is called as a overall phenomena of transformation of water, liquid water to the air, okay, as a vapor is called as a humidification operation. Okay, this is a natural process. This is a very natural process which will be happening near the water bodies. Wherever the small water stream also there, even a small pond which is there in our college also, this phenomena will be happening. Okay, wherever our sweat is there, okay, in our on our body, some sweat is releasing. Okay, whenever sweat is coming from our body, we will ask somebody to put on the fan. Why we are asking that one? Whenever fan we are putting off, the fan is just rotating and it will releasing some air. Okay, some convection is going on. Because of that air, the air is carrying out whatever the sweat which is there on our body. That's why we are feeling somewhat relief. So that is a humidification process. Everywhere humidification process is there. In the industrial sense, there will be some big cooling towers. Whenever you are passing through some power stations, okay, you might be observing the setups like this. Okay, a big cooling towers like this. Okay, whether it's a thermal power plant or whether it's a nuclear power plant, whatever it may be, you might be observing this type of units. That is nothing but a cooling units. In this cooling units, what happens? Hot water will be just sprayed onto the, some packing will be there. Hot water will be sprayed onto this one and the air will be entering from the bottom. Whenever air and this hot water will be coming intimate contact with each other, so they will be exchanging mass. Okay, they will be exchanging heat. Okay, some part of water will be transformed to the air like this. Okay, that is a cooling tower in the industrial operation. Whereas removal of sweat from our body by the air which is coming from the fan is the best example for this humidification operation. Then wherever the water streams are there, stream bodies are there, there the air which is passing by convection on top of this water stream, the transformation of this liquid to air is known as the humidification operation. Okay, this humidification operation we will be seeing in detail in mass transfer operation 2. Okay, is that clear?
Yes, sir.
Yeah. Then finally, after humidification process, what happens? We will collect this, one second. We will collect this sample of air and we will be defining how much amount of water. Okay, that is nothing but kg of water vapor which is present in the kg of air. Okay, that is called humidity. This much humidity we can able to transfer to the surrounding air. We can define like that. Yes. Yes, some doubt? Who is
Sir,
asking that?
sir, in humidification, where does the vapor will go, sir?
Where does the vapor will go?
Yes, sir.
Where does the vapor will go means this is on into the air only, no? It is coming to the air.
It will evaporate, sir.
Yes, it will evaporate. It will carry away. By the convection, it will carry away. It will carry away and it will
Okay.
go to the surrounding gas phase. So air is nothing but one type of gas phase only, no, but vapor will be present. Okay, you know the meaning of what is gas and what is vapor. I hope you know
Yes,
that
sir.
one. Otherwise, the phase diagram you have to refer once again. Okay, after critical point PC and TC, so the vapor will be transformed to the gas phase. So that's what I can say. Okay, is that okay? Shall I
Sir,
continue?
Okay, sir.
Yes, yes, yes.
sir, can you say the difference between evaporation and humidifications?
Evaporation and humidification. Okay, evaporation is not a natural process. Here you are not applying any heat here. Okay, here you are applying a heat in the evaporation, maybe through some steam. Okay, using some jacket heat exchanger you are applying, or otherwise you are directly giving some heat. But here you are not applying a heat. By the natural process of osmosis, the water which is present in the liquid phase is getting transformed to the surrounding gas phase. So that's a difference there. And plus here there is no solids. Okay, here there is no solids, only liquid is there. But here in the evaporation, there is a solids in the concentration of juice. Okay, the best example for evaporation is a concentration of juice. What happens in the juice when you just squeeze out? Okay, lemon. Okay, lemon or what we say this. Orange or lemon, okay, whatever the juices are there, when you squeeze out whatever the juice inside this one, so this will be present in a very dilute form. So dilute form means it will be some solute will be there. Solute is nothing but solids content plus some solvent. So solvent is nothing but water will be there here. So this water, now evaporation operation, what is the main aim of evaporation operation? To just evaporate the solvent which is present there and leave behind the solute. That is nothing but concentrated juice. So this is dilute juice. Initially, whatever we are obtaining, that is a dilute juice. After evaporating the water, okay, removal of water. For example, in the initial stage, okay, in a dilute juice, 90% water will be there and 10% solids will be there. Okay, after you are evaporating, the concentrated juice will contain around 60% solids and rest will be water. So like this is concentrated juice. Transformation of dilute juices to concentrated juice is the best example for the evaporation. Here the solids is there, but there is no solids in the humidification operation. A pure solvent is there. A pure solvent we can say, or pure water is there. Pure water nothing means it is not contaminated. Okay, but I mean to say is it is a pure phase of water. Okay, there solids is there, here no solids are there. Is that okay?
Yes, sir. Okay.
Okay, then anybody else? Okay, then we will go for the basic units now. So you know that what is the basic units and what is the derived units. I would like to cover once again basic units. So this unit system is very important in the mass transfer operation. Everything will be related to units. You have to convert n number of units here. So before that, I request you to listen carefully here. So what are the basic 5 types of basic units are there? So that is nothing but mass, length, time, temperature, and mole is the basic unit. So this is the unit, okay, or we can say quantity, we can say. And the symbol for each thing, symbols are major here. Why? Because many equations now, from now onwards, you are going to see many equations in the mass transfer. So better to adopt everything in a symbolic way. Okay, symbols are very much useful because equations cannot be said everything in the text. Okay, better to remember in the symbols. Symbols are very important. So quantity, symbol, and what are its units? Mass. Mass will be measured. Mass will be just denoted by units m. Then units of mass is kg or gram we can measure, or in the FPS units it is lb. Then length or distance we can say. So length or distance usually will be measured in capital L. So that will be the units of this one is SI units meters, or we can say centimeters, or mm also we can measure, or in the FPS units feet also you can measure. Then time is denoted by theta. So it will be in SI units seconds, hours, okay, minutes. We can measure time. Then temperature. So temperature will be measured in capital T. So units will be SI units Kelvin, then degree centigrade, degree Rankine, degree Reaumur, okay, then degree Fahrenheit. So these many scales are there. Then moles, mass, length, time, temperature, mole. Okay, what is the mole? Okay, mole will be denoted by N. Okay, mole will be denoted by N. So what are the units of mole? Can anybody say what is the unit of mole?
Moles.
Mole is mole only. Okay, mole is mole. Then these are the basic units. Okay, from the basic units, apart from these 5 basic units, everything rest, all the units which is existing in the universe will be the derived units. We have to derive somewhere that one. But these are the remembering units which are basic units. From these units, everything will be coming. Okay, the units which are coming in the mass transfer is, for example, the first one. Okay, to quantify, okay, in every operation, something is getting transformed to something. Okay, here, for example, in the humidification operation, from the liquid phase, water is getting transformed to the air phase. And in this distillation operation, from the feed, some solute is getting transformed to the distillate and distributing among the distillate and residue. Then in the drying, the moisture is getting transformed from the solid phase to the surrounding air phase, okay, surrounding fluid phase. Then in the crystallization also, water is evaporating from the liquid phase to the surrounding air phase. And in the evaporation also same, from the dilute phase to the surrounding air phase, water is getting transformed. And membrane separation. From one phase, something is removing. The contaminants is retained by the retentate, and the pure water will be sent to the permeate. And here in the adsorption operation also, the contaminants will be deposited onto the surface of the liquid. That is liquid to solid. Okay, everything is going to how to quantify this one. For example, here in the adsorption, how much amount of dye which is deposited on the surface of the solid. How to quantify that one? So how to measure that one? So to measure that one, we have a quantity which is called as a flux, which is known as a mass transfer flux. So what is this flux? Simply we will call flux this one, or we can call this as a mass transfer flux, whatever it may be. But in the normal terminology, we will calling that as a flux only. Okay, what is this flux? So it will be measured in molar flux or mass flux. Okay, either of the case it is same. Okay, molar flux. Flux is nothing but amount of species or component transferred, okay, from one phase to another phase, or from one region to another region, or from one place to another place, per unit area, per unit time, is called as a flux or mass transfer flux. So for example, in the molar quantities, we are measuring in a species. Molar quantities means the units of this quantity will be mole. So amount will be measured in mole. Per unit area means area will be in meter square. Then time means second. For example, this amount is amount of species we are measuring in mass quantities. So mass means measured in kg. Per area, anything is same, meter square, and time is seconds. So this is called as a mass flux units. This is called as a molar flux units. Molar flux units. So these are the quantities which are used to measure the mass transfer from one phase to another phase, from one region to another region. These are the quantities which are required. Okay, that is the flux. Okay, I forgot to cover this one, R values. Okay, this you just remember this one, and at some stage while we are solving the problems, I would like to continue this one. Okay, I forgot about that one. So not to cover that one here. So this is the flux. Okay, flux is nothing but the measure of how much amount of mass is getting transformed from one region to another region, or one place to another place, or one phase to another phase. That is known as a flux. The flux units will be in the molar quantities. It is mole per meter square second, and mass flux will be in kg per meter square second. So same things will be there. So various quantities will be there here. So that is, first quantity is mass, its units. For example, I already stated you in the mass transfer operation for your syllabus, only two component system. Only two component system. So largely these two components we are denoting with A and B only. Okay, we are denoting every symbol. Okay, every notation we are using with A and B only. What is this two component system? Is any type of operation, that is distillation or humidification, evaporation, whatever it may be. So your system will be composed of only A and B only. So either of the case, okay, when A and B is present, among these two, one will be the solute, or A will be the solute, or B will be the solute. So among this one, we have to separate any one component. So that is our mass transfer operation. For our syllabus, UG syllabus, it is only assuming that only two component system are there. So you need not to worry A plus B plus C plus D, that you do not worry. Only A and B components will be there. So for component A and for component B, then total mixture. Total mixture is nothing but, so your total mixture is only two component system is there, A plus B. Okay, so in the system there are only two components, that is one component is denoted by A and another component is denoted by B. So individually, what are the notation scheme for A and what are the notation scheme for the B, we have to define. For example, for the component A, we want to define the mass, okay, in a symbolic way. How do we do that one? So mass is measured in kg or gram, whatever it may be. So for component A, the symbol of this mass is, so one more we can add symbol. The symbol will be M. That is M I species. I means A or B, whatever it may be. So M subscript capital A, and for the component B it is M subscript capital B. And total mixture means there are only two components in the total mixture, A and B. Then since this is a scalar quantity, mass is a scalar quantity or additive property, so we can define as M is equal to MA plus MB. Okay, this one is clear what I am trying to say, the notation scheme.
Yes, sir.
Okay, yeah. Then everybody please try to understand. If you understand this notation scheme, the derivations are very, very easy, dead easy. If you don't understand this notation scheme, they are very hard. Okay, only you have to mug up. How do you mug up? I don't know, but know the concept first. So mass is there. For the mass, symbol we are taking is a M. Okay, for each species, that is ith species, I will take a value of A or B. Okay, it is measured in units kg. Then for component A, for example, somebody is asking you what is the mass of component A, then immediately you have to define it as a MA. Then somebody is asking you what is the mass of component B according to our notation scheme, you have to immediately tell that it is M subscript capital B. Then what is the total mass of your system or total mass of your mixture in the mass transfer operation, somebody asked, means you have to say M is equal to M plus MA plus MB, because only two components are there in our system. That's the way you have to define that one. So next property is a velocity. So velocity, how do you define the velocity, or how do you denote the velocity? That is small u. Okay, small u. For each species it is I, ui, u subscript small I. Then units of velocity is mass meter per second. Then for the component A, how do you define the component A velocity? You have to define u subscript capital A. And for the component B, it will be U subscript capital B. Then the total velocity. Can anybody say what is the total velocity of the mixture A and
U
B?
equal to UA plus UB.
No, it is wrong. So, okay, these are the scalar quantities. Scalar quantities means we can add M is equal to MA plus MB. They are additive properties, but velocity is a vector. You have studied no in the physics. Velocity is a vector. It will have a definite direction. Okay, in which direction this velocity is acting? X direction it is acting, Y direction it is acting, or Z direction it is acting. So we cannot define U is equal to UA plus UB because it is not a additive property. U is equal to, for example, UI in the X direction plus UI in the Y direction plus UI in the Z direction. Whenever you are defining a velocity, you have to define it whether the velocity is in X direction, okay, velocity is in X direction or Y direction or in the Z direction. You have to define clearly. Then only we can find out what is the total velocity. But individually, when there are quantities are there, we cannot find the vector quantities. Okay, vector is having some definite direction, but scalar is not having any direction. Okay, this is from physics. So this is UI. So the total mixture we cannot tell. Only individual components we can tell for that one. So velocity is there. The next one is a volume. So volume will be denoted by capital VI. Okay, capital VI. So volume units will be meter cube. Okay, volume units will be in a meter cube in a SI units. Then for the component A, what is the notation scheme? Capital V subscript capital A and capital V subscript capital B. Then can anybody say the total mixture volume? Please don't hesitate, just interact, don't hesitate to say. If you are wrong, that is nothing. Wrong is also okay. So we will commit a mistakes. We are human beings. Please try to interact. Please try to interact. What is the total
A plus
mixture volume? VA plus
VB.
VB. Okay, this is also additive property volume. So that's why we can able to calculate for the total mixture VA plus VB. The next one is a molecular weight. Okay, this is also a well-known quantity for you, molecular weight. So molecular weight will be denoted with capital M, I for the ith species, capital MI, subscript small I. Then the molecular weight will be having a units of kg per kg mole or gram per gram mole, whatever it may be. Then for the component A, it will be capital M subscript capital A. Then for component B, it is capital M subscript small capital B. Then what about the total mixture molecular weight? Can anybody say? This you have already covered in CPP course. Without this formula, no CPP, you cannot do the CPP course. Many times you have to use that one. What is the total mixture molecular weight? Can anybody say?
MA plus MP.
No. You have to, you already used this one, average molecular weight. Do you remember this one, average molecular weight? Sigma
MA
I
plus
is
MP.
equal to 1 to N Xi into Mi, mole fraction into molecular weight. You know this one? Have you seen this formula?
Yes, sir.
Okay, CPP, this is the basic formula. You have to use this formula every time for the mixture properties. Okay, this one is for the molecular weight. Then next one is the moles.
Sir,
Moles is denoted by N. Yes.
can you please once again explain molecular weight formula, sir?
Okay, molecular weight. Okay, yeah, I will explain. Don't worry. So molecular weight. So what is this molecular weight? How do we denote this one? M. Okay, what is the meaning of this M? Molecular weight means weight. For example, from the moles relationship only it is coming. Moles is equal to, you know what is mole? Mole is nothing but weight divided by molecular weight is nothing but moles. So what is molecular weight then? Molecular weight is equal to weight by moles. So what is the unit of weight? Which is kg. What is the unit of moles? Which is kg mole or mole. So kg per kg mole will be the units of molecular weight. So for when there is in a system, there are two components only. Okay, molecular two components only, A and B. So their masses are Ma and Mb, but their molecular weights are denoted by capital Ma and capital Mb. These masses are the additive properties. They are scalar quantities and additive properties. We can define total mass is equal to Ma plus Mb, whereas molecular weight is capital M, total molecular weight, Ma plus Mb. If you define this such a way, for example, your A is, let us take your A is some hydrogen, okay. Then B is a helium. Okay, simple component we will take helium. What is the molecular weight of hydrogen and helium? Molecular weight of hydrogen is
1,
1. Molecular weight of helium is
2,
2. Then what about mixture? If this is a mixture, helium plus hydrogen is a mixture. Then if somebody is asking you to calculate total molecular weight of this helium and hydrogen mixture, then you have to perform 1 plus 2. If you perform this one, your molecular weight will be 3. Okay, this is not a valid relationship. For example, when somebody is asking you to calculate the total mixture molecular weight, you have to ask them first, what is the composition of hydrogen in the mixture? What is the composition of helium in the mixture? For example, this gas, okay, gas mixture is there composed of hydrogen and helium. Then hydrogen is present as a 20% and helium is present in the 80%. Then that type of problem is a correct problem. Then they have defined every quantity we required. Means the mole fraction. If this quantities percentages are defined in the moles, then we can say this is a mole fraction. The mole fraction of helium. So xi, or we can say x. For example, hydrogen is a xa is equal to 20 divided by 100 because it is a percentage 0.2, and xb is equal to 80 divided by 100, which is 0.8. Then you have to perform this operation. Average molecular weight. There is no total molecular weight, only average molecular weight for any type of mixture. So that is sigma I is equal to 1 to n xi into mi. For your system, only two components are there. So two component means that I am writing once again, that is I is equal to 1 to n means only two components are there. So xi into mi. So for the first component, when you are writing molecular weight, that you have to define xa, ma. Then one another components are there in your system, that is xb and mb. Then it is xa is 0.2 into ma is hydrogen molecular weight 1 plus xb is 0.8 into the molecular weight of helium is 2. Then what happens? 0.2 plus this one 0.8 into 2 is 1.6. So this is 1.8. Okay, they see this one is average molecular weight. So average molecular weight when it is crossing. So okay, this molecular weight of one component is 2, molecular weight of other component is 2. If the average molecular weight is crossing more than this quantity 2 or 1, so that is not a correct quantity. So average molecular weight will be calculated in this manner. If you have a 3 component system, so the meaning of this one is sigma I is equal to 1 to n xi into mi. The meaning of this one is sigma I is equal to 1 to n means now it is 3 components, that is xi into mi. Then you have to write xa ma plus xb mb plus xc mc. But you don't have to worry. Why? Because in our mass transfer operation, we are not considering third component. Only two component systems we are assuming here. For your syllabus, only two component system is there. Is that okay? Average molecular weight.
Yes, sir. Thank you, sir.
Yeah. Okay, this is the quantity. Okay, time is up. So tomorrow we will cover this one. Okay. Yeah. Okay, I hope no doubts until now. Is that okay, everybody? Please, please,
Okay,
Clear,
sir.
please
sir.
try to interact every time. Okay, these are very, very important principle in your heat transfer also. Whatever the next courses you are going to do, in every course, these quantities are coming to play a very major role. Okay, better to just clarify then and there you